Okay, I'm coming back to this problem, and I was looking at it real quick, and I went through the section. I realized, well, hold on a second. We have another test in here that I have not used this entire homework set, but it's part of this section, and it's in your comparison test. There's three parts. There's one, there's two, and there's a third part. And this last part is what's referred to as the limit comparison test. And this test is really nice because what this third one says is that let's say we're comparing that to this, okay? And remember, this is going to be our a sub n. The limit comparison test says if the limit as n goes to infinity of the ratio of a sub n over b sub n. So you take this and you divide it by this. If that turns out to be a number, where c is a positive number, then whatever this one does, this one does. Okay, so if this diverges, that one diverges. If this one converges, that one converges. Now, there are several problems in this section I could have done using this. But I forgot that this test was in this section. I thought it was in the next section for some reason. So what I need to do is try and come up with something to compare it to, and then take a look at that limit, that ratio. And so I'm going to use something that I really kind of remember from Cal 1, and that's if you look at the sum n equals 1 to infinity of 1 over n, I know that if I put 1 over n under this and do a limit, I know that's going to turn out to be something very nice. But let's first talk about this one. This is a harmonic, and it's divergent. So this is going to be my b sub n, and those are positive numbers. This is going to be my a sub n. Are those positive numbers, though? Well, we know sine oscillates back and forth, right? However, if I plug in like 1, I get sine of 1, and then I'm going to go plus sine of 1/2, then plus sine of 1/3, and then plus sine of 1/4, and I'm going to keep doing this forever, right? Well, these are angles. If we look at the unit circle, this right here is pi over 2, and this is pi. And 1 is smaller than pi over 2, so this first angle is somewhere over here, and then half is somewhere smaller, and 1/3, and 1/4, and 1/5. So all of these angles we're plugging into sine are in the first quadrant, and the value of sine in the first quadrant is always going to be greater than 0. So I know that all of these numbers are positive numbers, so I can use this test. All right, that was an important thing to remember, that these have to be positive numbers, or they could be 0 also. But so this is true. So I'm going to take the limit as n goes to infinity of the a sub n over the b sub n. And when I do that, 1 over infinity goes to 0, sine of 0, 0. 1 over infinity goes 0, I get 0 over 0. So I could use L'Hopital real quick. Again, I'm supposed to switch to x, but I'm not going to. The derivative of the top is cosine of 1 over n times negative 1 over n squared, chain rule. Derivative of the bottom is negative 1 over n squared. These two cancel. And now if I let n go to infinity, I get 1 over infinity is 0, cosine of 0 is 1. So I'm getting that this limit is 1. And remember, for the limit comparison test, we needed this to turn out to be a constant, a positive number, which it is. If this turns out to be a positive constant, then whatever this series did, this series is also going to do. So therefore, sum n equals 1 to infinity of sine of 1 over n, since that diverged, this one will also, diverges by what we'll call the limit comparison. test. This is a very nice test. So I would hope that this kind of looked familiar. In Cal 1, if you ever had sine of something over the same thing, and both of these went to 0, this was a very special limit that you learned at the beginning of Cal 1 that they tell you, okay, that limit is going to be 1. Now, I showed it by L'Hopital's rule that it's 1, but that's why I chose 1 over n, is because of this thing. All right, that's kind of cool. So 30, number 30 is going to be the same test. We're going to use the limit comparison test again. And then I think what I might do is go back and take a look at a couple of other problems you could have used the limit comparison test on. Let me do 30. Sum n equals 1 to infinity. N plus 5 over the cube root of n to the 7th plus n squared. And that's not very good looking, is it? So let's try and figure out what we would want to compare this to. How about we compare this to whatever happens if n gets real big over there? Something like, the top would be like n, the bottom would really be like the cube root of n to the 7th. And so what I'm going to do now is instead of trying to figure out what this, get these inequalities and try and do this thing or this thing, I'm going to try and use a limit comparison test instead. So let me figure out what this does. This is going to be a p-series. This is n over n to the 7/3. And this is sum n equals 1 to infinity. Let me see. I can't do simple math right now. This is 3/3 minus 7/3, negative 4/3. So 1 over n to the 4/3. That's a p-series with p being 4/3. That's bigger than 1. This converges. So I have a convergent p-series over here that I'm going to compare it to. But I'm going to do the limit comparison instead of the regular comparison. It's my a sub n, that's my b sub n. Actually, I'll do this as my b sub n. This is positive. This is obviously positive also. So now let me do my limit. Take the limit as n goes to infinity of my a sub n over my b sub n. It's going to look ugly. Let's do this. Let's do n over cube root n to the 7. Let's do that. So I'm using this one up here. And then what I do is before I do my limit, I'm going to flip this one up. So we get equals limit n goes to infinity. See, when I flip this up, I get one fraction. I'm going to have an n plus, I'll do it this way, the n plus 5 up top, that's this. What came up to join it is this one. So times the cube root n to the 7th over, now I had the cube root of n to the 7th plus n squared times, and this n joined it on the bottom. And now what I'll do is again, I don't want to use L'Hopital yet. Try and put some things together here. That's equal to limit n goes to infinity of, watch, I'm going to put these two top of one another, so n plus 5 over n times, and then since these are both cube roots, I'm going to put them all underneath a cube root. And I'll get n to the 7th over n to the 7th plus n squared. And now, of course, if I let n go to infinity, I'm going to get infinity over infinity. In here, infinity over infinity. So I'm just going to go and just on the side and almost mentally do a L'Hopital's rule on this. Okay, so this is like two different limits now. L'Hopital on this, I'm going to get a 1. Times, now I'm going to do L'Hopital on the inside of this, like on the side. I'm doing like limit, n goes to infinity, n to the 7th over n to the 7th plus n squared. If I do L'Hopital, I'm going to have to do L'Hopital a few times, and I'll get 1. So I know that this goes to the cube root of 1, which is just 1. So this whole thing, this whole limit turns out to be 1, which is a positive constant, right? This is a constant, it's positive. So that means that whatever this series did, that one does also. So therefore, it converges. Therefore, series n equals 1 to infinity, n plus 5 over cube root n to the 7th plus n squared converges by the limit comparison test. So let me see what other ones we could have gone back and done. Let me see here. How about number 26? This is the one I said we could show its harmonic and just be done with it. On 26, sum n equals 1 to infinity, 1 over 2n plus 3. If I compare that to a harmonic series, if I compare that to 1 over n, I know that this diverges. I'm going to go through this very quickly. And this is positive and that's positive. So if I take the limit as n goes to infinity of this guy, 1 over 2n plus 3, over this one, 1 over n, and I flip, and I get n over 2n plus 3, then I do L'Hopital, I'm going to get 1/2. And this right here is a constant and it's positive. And that's what I need for me to draw my conclusion. So whatever this one does, that one also does. So that one would diverge. And we knew that. Let me see if there's another one that we could have done using that one. Jeez. Could have done 25 also, that way. For 25, we had 1 plus 4 to the n, 1 plus 3 to the n. Remember that one? And that one we did by the nth term test. But let me just show you if we compare it. If we compare it to that 4 over 3 to the n, this is a divergent geometric series. So we would do limit n goes to infinity of this guy over this guy. I'm going to write it this way, which is limit n goes to infinity, and when we flip, we get 1 plus 4 to the n over 1 plus 3 to the n times 3 to the n over 4 to the n. And then I could split this up and do something like limit n goes to infinity of 3 to the n over 1 plus 3 to the n times 1 plus 4 to the n over 4 to the n. And then when I do L'Hopital, I can do L'Hopital, since it's product, I can just do L'Hopital on each one. So I would get something like limit n goes to infinity. L'Hopital on this would give me 3 to the n times natural log 3 over 3 to the n natural log 3 times, this one would be 4 to the n natural log 4 over 4 to the n natural log 4. And then these cancel, and then that's a 1, and then that's a 1. So this all equals 1, which is a constant, and it's positive. So whatever the original, whatever I compared it to does, this one does. Remember I compared it to a divergent geometric series, so that's going to be divergent. See if there's any others that I would want to do that way. I think that's probably good enough. Just to show you how that's just to show you how that limit comparison test works. All right, well, that's 8.3. I hope that all makes sense. Good to go.